Welcome viewers. Previously we looked at capacitors and we said capacitors are devices that we can use to store charges. To store energy or charges. And today we want to look at the charges, the effective capacitance that a capacitor can store when they are connected in series. Now, in series connection, capacitors are connected one after another, and we have the source of electromotive force, which can be simple dry cells connected in series, also forming the battery. So suppose we have only two capacitors which are connected one after another in series. Then the first thing is the charge that will develop on capacitor 1. Let's call it Q1. And the charge which will develop on the plates of capacitor 2 is Q2. But the total charge from the source is Q. Now, it can be proved that charge 1 is equal to charge 2 and is equal to the total charge, which is the charge from the source. So let's have that as our equation 1. Q is equal to Q1, which is equal to Q2. Now, these capacitors will be having voltage drop across them as we pass or as we put on the switch. So the potential difference across capacitor 1, C1, is V1, and the voltage drop across capacitor 2 is V2. Now it can be proved that the sum of V1 plus V2 is equal to the total voltage from the source, which is V. So V is equal to V1 plus V2. That gives us our second equation. Now recall that from the definition of capacitance of a capacitor, capacitance is equal to charge per voltage. Charge per voltage. So mathematically that can be expressed as C is equal to Q over V. Now if we make V the subject of the formula, then V is equal to Q over C, where V is now representing the total voltage from the source. Q is representing the total charge within the circuit, and C represents the effective capacitance for these capacitors which are in series. Now, from here we can now see that V1, which is the voltage drop across capacitor 1, is equal to Q1 over C1, right? And V2 is equal to Q2 over C2. Now, when we now substitute this into the equation, V is equal to V1 plus V2, we now obtain Q over C is equal to Q1 over C1 plus Q2 over C2. But remember, Q is equal to Q1, which is equal to Q2. So this equation can be expressed as Q over C is equal to Q1 over C1 plus Q now over C1 plus Q over C2. So we can factor out the Q, and we now have the equation Q over C is equal to Q out of bracket into 1 over C1 plus 1 over C2. So Q can cancel out, and finally we are left with 1 over C is equal to 1 over C1 plus 1 over C2. whereby this now gives us the equation which we can use to calculate the effective capacitance for these capacitors in series. 1 over C is equal to 1 over C1 plus 1 over C2. Now, for example, consider a circuit having two capacitors. Capacitor 1 or being 4 microfarad, capacitor 2 being 8 microfarad. Now, if we are supposed to obtain the effective capacitance for these capacitors, then we now use the equation 1 over C is equal to 1 over C1 plus 1 over C2. So making substitution, 1 over C is equal to 1 over 4 plus 1 over 8. Then we obtain the LCM between 4 and 8, and the LCM is 8. So 1 over C is equal to, 4 goes into 8 twice, and 2 times 1 is 2. So we have 2. Then 8 goes into 8 once, and 1 times 1 is 1. So we have 2 plus 1 over 8, which is equal to 3 over 8, being equal to 1 over C. And remember, C is the effective capacitance. So making C the subject of the formula, or if you cross multiply, then it means that 3C is equal to 8. 8 times 1 is 8. Therefore, C is equal to 8 divided by 3, which gives us 2.666 recurring. So we can make it to be 2.67 microfarad. Now, in summary, when we are talking about capacitors in series, remember always that the charge across each capacitor is equal to the total charge from the source, and the charge on capacitor 1 is equal to charge on capacitor 2, even if they are 4, 5, 6. The charge across each one of them is the same or is equal to the charge from the source, and that is our equation 1. Okay, Q is equal to Q1, which is equal to Q2, which is equal to Q3, and so on and so forth. Then the PD, the voltage drop across each capacitor when they are in series, is the sum. When you add them up, is equal to the total electromotive force from the source, where V is equal to V1 plus V2 plus V3 if there are 3 capacitors. Effective capacitance, C, 1 over C, is equal to 1 over C1 plus 1 over C2. Okay, so in a special case, if there are only 2 capacitors, we can have a general formula for calculating the effective capacitance. If you consider the LCM of C1 and C2, the LCM of C1 and C2 is the product of C1, C2. So that is our LCM. Now C1 goes into C1, C2, C2 times 1 is C2. Then C2 goes into C1, C2, C1 times 1 is C1. So we have 1 over C is equal to C2 plus C1 over C1, C2. So if you make the C the subject of the formula, C will now be equal to the product over the sum. The product over the sum, meaning that C is equal to C1, C2 over C1 plus C2. And that only works when you are dealing with 2 capacitors, only 2 capacitors. Now, if there are more than 2, then that equation of effective capacitance being equal to the sum over product does not apply. To that end, we come to the end of our discussion today, but for more such discussions, I invite you to subscribe so that you don't miss out, because next time we look at now capacitors in parallel. Thank you very much, but remember to subscribe to this channel.